My dear students, and welcome to this final revision lecture covering the 12 weeks we have spent together in the solid state electronics course. Today, we are trying to make some sort of a brief revision to the main or the most important points across the module. I will start first with giving you some general outlining to scan or flashback in a very quick manner the main lectures we have studied together in this module. Then we are going to talk about the final exam, how it will look like, its main outline, its main headlines. And finally, we are going to solve some problems, some uh, uh, discrete problem, let me say, covering different topics in the module. So now, please accept my invitation to start sharing my screen and start together this short revision lecture dealing with the solid state electronic course. That's perfect. So let's now start with flashback on the main topics covered in this module and the lectures and the tutorials. So let me now share screen and go directly to your e-learning page. As you can see, this is your e-learning page. So let's start with lectures. So we have, of course, the first lecture is was an introduction lecture. Then we have let me say, three lectures dealing with the semiconductor material fundamentals, starting with semiconductor material fundamental, mass action law, and energy bandogram. Of course, this is the first important, or let me say, this is the first very important bulky part in the module. I believe I will go more in a detailed manner later on when I discuss the final exam and the content of the final exam. But principally, this is a very important part. You will find a lot of questions, maybe 35 to 40% of the exam will be covered by these three main lectures. Then we have the device part. So we have in this module 4 devices, which is the other 60% of the final exams, of course. So we have the PN junction, the MOSFET, and finally we have the bipolar junction transistor and the tunneling field effect transistor. One of the questions that I received a lot during the mid break in Jan or even in February is that we don't have a tutorial problem on lecture number 6 and 7, and actually this was already mentioned during the lecture that these two devices or these two lectures will be only covered in the lecture, and they will not be a corresponding tutorial for these two lectures. So what you are going to learn is mainly what you have already learned during the lecture, or what some problems or some conceptual parts, as you know. And also I will mention this later, that part of the exam will be a analytical part, I mean problem solving part, and another will be a conceptual part. So whenever you have questions related to the BGT or the tunneling field effect transistor, please expect that these questions will be somehow conceptual or following the same trend you have already learned in the lecture. So you don't need to have more questions. However, please feel free to access the solid state electronics reference bar treatment in order to address more about these two topics, or maybe to solve more problems about these two topics. So this is the part of the lectures. Here are all the corresponding lecture scripts, as you know, and this also all the lecture videos already over the YouTube, as you can see me now, or you can access them from the e-learning page. And then we have the this is the animation part, of course. And now this is the tutorial part. I think all the tutorials were with solutions are available up to the MOSFET part. No more data about the project because you already got the grades. And finally, also you have the unseen final exam, the previous unseen year final exam. This is maybe a good template because somehow we will follow the same structure, and also it may be a good exercise to solve more problems using this template also. So this is simply the structure of the module. I believe that most of you already have passed across all of these documents before, so this is just a quick flashback on the module content. And let's now start going into the exam structure and how we are going to solving the exam, what is the perspectives, or what is maybe my tips or my guidance for you before the final exam, inshallah. Okay, so let's start with the previous year unseen exam, and let's consider it somehow as a reference or as a template for this year unseen exam. So let me now share again my screen in order to have a look on this. Okay, so this is a previous year final exam. As you can see, we have one question. If you read this paper in a very detailed manner, you will find that we have one question, which is an obligatory question. We will call it question A. And then we have three questions where you are asked to select two out of these three. Actually, what is somehow different this year with respect to the previous year is that in your final exam, you will not find A1 and A2. It will be one question, which is called question number A. And this question A will have 32 mark, not 34. So in the previous year exam, it's 18 plus 16, which is 34. However, in this year, it will be a one question exam covering 32 marks out of 100. And again, this is an applicatory exam, question. Usually, actually, I prefer to make this first question covering one of the first part of the course, because I usually believe that these parts are well understood with respect to others. Most probably you have already studied this part before during your in-class test. So I prefer to make it easy for you, I usually prefer to put my first obligatory question on this part, which is typically the first three lectures, because this one is an introduction lecture, so it's lecture number 0. So this is the first three lectures are usually covered by the first obligatory question. I believe this is the best way for you because, as I mentioned, you already studied this part more than one time, so it should be well digested, well understood from your side. I believe so, or I assume so, let me say. So that's why I usually put the first question in this part of the book. Then we have a set of three questions, each one with 34 marks, and you are asked to solve two questions out of four. You are asked to solve two questions out of four. So, how are these? Two questions out of three. I'm very sorry. Two questions out of three. I'm sorry. So, how? Let me first show you this in the previous exam as a reference. So here, if you can go down, you will find question B1, and then question B2, and then question B3. So you are asked to solve two questions out of three. Each one has 34 marks. So 34 plus 34 plus 32, which is typically 100. So how these questions will be divided. So usually, again, I divide the course into three portions. The first portion is typically the one I just mentioned, which is sorry, let me erase this. So this one. So this is the first portion, which is the material portion. As you see, this includes the first three lectures in the module. So you will find one of the three optional questions on this part of the module. So this is the first part to be asked in the optional. And then for the other two questions, you will find that we will have one question which will cover the p-n junction and one of these two topics. And the other question will cover the MOSFET and one of these two topics. So as I just mentioned earlier in this lecture, these two lectures are somehow conceptual. So most probably you should expect a conceptual question dealing with these two lectures. But our main two devices are the MOSFET and the p-n junction. So you will have one question mainly about p-n junction, with a conceptual question about one of these two topics, and then another question about mainly about MOSFET with another small conceptual part dealing with one of these two topics. So this is basically how the exam will look like. So now, if you recognize my words well, you will understand that these okay, sorry, these three first lectures in the module are somehow very critical part of the module, because these three lectures will include an obligatory question of 32 marks and an optional question of 34 marks. So you can guarantee about 66 marks of the final exam, which is two-thirds of the final exam, if you study well these three chapters. That's why I'm pushing you toward studying well these three chapters. Again, I believe that these should be the most or the highest digested chapters in the module, because you already have a good experience with them when you study for your in-class testing. So this is simply how the final exam will look like. So let's now go more toward technical parts, and let's make some sort of scanning about some important problems. I will use the previous year exam as a reference in order to solve some problems with you. I hope that these problems give you some sort of refreshing for your memories. I believe that you have some sort of a gap for something like 1.5 months, and you need some sort of refreshing back to your minds in order to restart remembering what you have already learned in semester one. So let's go through this step by step. So, for example, one of my announced secrets with you is these problems related to the energy bandogram. If you remember, my dear students, we already have discussed this before. I told you in this lecture, this is typically, if I remember, it's lecture number 3. I think this one. Yeah, we can open it. Okay, if you remember, during this lecture, which is lecture number 3, we have already go together and solve a problem. Yeah, typically this problem. And I told you that please expect to see this energy bandogram. Of course, I don't mean this specifically energy bandogram. I mean this kind of problems with energy bandogram in your in-class test and in your final exam. And in order to prove to trust me, this is the final exam for the previous year, and you can see this is an energy bandogram. Of course, you will have another new energy bandogram in your final exam, but still you have the same procedure of solving. How you can get these different parameters and these different important points using the energy bandogram you can see. So let's start now solving together this problem as some sort of refreshing back our knowledge about solving problems related to energy bandogram. Okay, as you can see here in this case, we have this energy bandogram, and the first requirement is to plot the electrostatic voltage, or it can be named also the electrostatic potential. So both have the same meaning. And if you remember, my dear student, if you remember, I usually told you, whenever you have an energy bandogram, please expect to plot the potential, the electrical field, and also the charge accumulation. These are basically the main outputs that you can plot from the energy bandogram. So let's now return to my paper here, this whiteboard. So, okay, we'll need to have it here in my screen. Okay, that's perfect. So as you can see, we can make some changes also in order to have both. Okay, that's perfect. Yeah, now everything is settled on my side. So now, as you can see, this is our energy bandogram. So we have an energy bandogram looks like this. And again, this is Okay, so this is the, of course, the valency band, and this is the conduction. If you remember, my dear students, I usually told you it's very simple. Energy and potential are inversely proportional, if you remember. If you have an energy bandogram like this, so that's basically mean that when you have an electron here, this electron will move in this direction because electrons slides, however holes climb up. So now electrons will move in this direction. That means that this is a positive direction and this is a negative direction. So if you would like to plot the energy, or sorry, if you would like to plot the potential or the voltage, it will be typically in the other direction. Very simple like that. So back here, if this represents the energy, then basically the potential is vice versa. How can we make it? It's very simple like that. So let's divide it into portions and let's start to inverse each portion individually. So this is a positive slope like that, it will be a negative slope like that. This is going up, then this will go down. This is going in this direction, then this will go in this direction, and then this is like this. So this is typically the inverse of this one. This is typically how we can plot the energy of your, sorry, the potential of your energy. So this is the energy, and this is the V, or the potential. Again, it's directly the inverse of this structure, just the inverse. Here we have a positive peak, so here you have a negative peak. Here you have a negative peak, then here you have a positive peak. Here you have another positive, then here you have another negative. So it's directly the inverse of this structure. This is the potential again. Okay, so this is one step. Let's return back to the question, please. So let me start sharing again. Yes, I believe you still now. I think you can now see my the exam paper. So let me check. Okay, that's perfect. So this is the first question, is to plot, to sketch the electrostatic potential. Determine where the semiconductor is degenerate. Again, you have to refresh your knowledge. So what is a degenerate semiconductor? First, in order to study, to understand the degenerate, you have first to remember what's called the Fermi level, this horizontal line. And again, please remember that whenever the Fermi level is in horizontal line, that's typically mean that your device is under thermodynamic equilibrium, which is the case. As you can see here, you have a Fermi level, and then the Fermi level is typically horizontal, then your device is under thermodynamic equilibrium. Okay, but our question is about the degeneracy. Is this device, or is this where at which part of this device the energy bandogram is a degenerate, or the semiconductor is a degenerate? So a degenerate semiconductor is a semiconductor with a very high doping. So let me return back to this slide to make some sort of refreshing to your knowledge. Okay, perfect. So typically for a semiconductor, we have the conduction band, the valency band, and we have the Fermi level. If your semiconductor is an intrinsic Fermi level, I mean this semiconductor without any type of doping, then you have this EF equals to EFI, which is typically in the center of the energy gap. So I mean, this is EG over 2, and this is EG over 2. So this is the typical intrinsic semiconductor material. However, if you go for an N or a P doping, then your Fermi level will start to move either upward toward the conduction band if it's an N type, or downward toward the valency band if it's a P type. So for N type, for example, you will have something look like this. So now the Fermi level is more toward the conduction band rather than to the valency band, because the number of holes, sorry, number of electrons is greater than number of holes in n, is n is greater than b, if you remember. So this is very, very, very important. Then, of course, inversely, you can say it in the p time. So this is the intrinsic Fermi level, and this is the Fermi level after the p2. Okay, so here p is greater than n. So now this is the general formula. As you know, this region, I mean the distance between the Fermi level and the conduction band, or the distance between the Fermi level and the valency band. This region is proportional to the doping. This region is proportional to the doping. If you remember that rule, this actually you shouldn't memorize. It will be given in the formula sheet if you need it, saying that the n, or the number of electrons, is equals to what's called nc e power ef minus ec over kt. So from this you can say that whenever you have higher n, then you have this is goes more and more lower. I mean, EC minus EF starts to decrease. So whenever you increase the doping, this N will go more toward the conduction band. So, or accordingly, if you have a very, very, very high doping, this F will go to be something like to tangent, to overlap the conduction band. Herein, we call this a degenerate semiconductor. So a degenerate semiconductor is a semiconductor where the distance between the conduction band and the Fermi level, or the distance between the conduction band and the the valence band and the Fermi level is smaller than 3 kT. If this distance is smaller than 3 kT, we call this a degenerate semiconductor. So if you remember, this kT is equal, kT over Q is equals to 25.9 milli electron volt at 300 Kelvin. If you remember this is a constant. You will find it in your constant list in the last page of the exam. I will show you it later on. But this is very important. Also, please remember that K, this Boltzmann constant, could be either in the electron volt format, so you don't need to divide by Q, or it can be in the joule format, so you have to divide by Q in order to transfer it to electron volt. So this is basically the case. But in our case, in our exam, we don't have a lot of numbers. We are not able to recognize if this is somehow greater or smaller than 3 kT. So you have to make it in a very easy manner. You have just to search about the place where your energy bandogram is just overlapping, or sorry, your Fermi level is just overlapping with the valency band or the conduction band. If you scan by your eye now this, you will find, for example, this point. If you remember, this is a Fermi level, and this solid black line is a valency band or the valency level. So in this point, the Fermi level overlaps over the valency band, the valency level and the Fermi level are overlapped. Then at this point, which is L equals to L over 4, the material should be degenerate. So simply the answer for part number B is is X equal L over 4. Of course, I elongate the answer in order to make some sort of refreshing for you, but you are intelligent enough that in the final exam, you have just to search for this point where EF and EV are overlapped, and then this is the degenerate point. Now sketch the electrostatic, sketch the electrical field as a semiconductor. This is the next requirement. If you remember, in the part number A, we say that this is typically the inverse. The voltage is the inverse. What about the electrical field? The electrical field is very easy. The electrical field is typically the differentiation of this curve. So let's do it together now. Okay, let's stop. Okay, let's stop sharing for a while and let's go to now here. So Okay, that's perfect. Let's first start to plot again the energy bandogram. And that's now, this is energy, of course, and the unit is electron volt. And this is the x-axis. Now, what you are going to do is to plot x again, but now you are going to plot the electrical field. Usually the unit, usually the unit of the electrical field is voltage over centimeter, or voltage over meter, unit meter, or unit length. So this here we have, this curve can be divided into 1, 2, 3, and here is 1, 2, 3, 4. This curve can be divided into 4 portions. Of course, whenever you have a constant, the differentiation for a constant is 0. Whenever you have a positive slope, then you have, of course, the first derivative of a slope over, of course, I'm sorry, the first derivative of a line is the slope. So whenever the slope is positive, then you have a positive value. Then here we have a negative slope, then you have a negative value. And then here you have another positive slope, then you have a positive value, and then 0. So simply, this is the electrical field. Typically, when there is no variation, when there is no applied voltage, there is no electrical field. If you remember, the sign for a voltage is that we have a tilting, like this. This is a tilting. So whenever you have a voltage, you have an electrical field. This electrical field could be a positive or could be a negative, of course, but there is an electrical field. But if there is no voltage applied, like in this area, there is no electrical field. This is simply the model answer for this part. So let's go to the